And we missed how much? Almost 15 minutes. It's okay. I'll post the notes PDF. So it's a continuous version of the power series. And what does it do? So again, this time you have a box or, transformation. The input is this guy. So on one side, you're sending functions of t, and it doesn't have to be continuous. And on the other side, it's the value of this integration. All right. Now, that integration at the end, it's a function of a specific letter. What letter is that? I mean, it's one of those letters you see in that integration. So the final result, the output of that machine, it's a function of... Anybody? Anybody? At least type something that I know, someone is listening. Damn, S, good. So it's a function of S. So I'm going to call that function capital F of S. There we go. That was the story of Laplace transform. In fact, that's the motivation. Okay, so what is it? It's a transformation that on one side you're sending real valued functions f of t, and on the other side it gives you a function of s. I'm going to call it capital F of s. Okay, now let me tell you one simple application. So suppose this is the space of all these functions, all the f of t's. Okay, and on this side you have all the functions, all the Laplace transformations of f of s. Okay, let's say we have a differential equation on this space where unknown with f of t as unknown, right? For example, f double prime plus 5 f prime minus 7 f equals, e to the t cosine of t, right? That was a non-homogeneous second order linear differential equation we learned in chapter 5, okay? And we know how to solve it. Now, this is the power of Laplace. With this machine, with this transformation, you can send this into this space and becomes not differential equation. That's the nice thing about it. Because remember, right now, this guy is a differential equation in terms of f. But when you transform this into this space, it's not differential equation anymore. I mean, you'll see it on Monday, how it works. So you get just an algebraic equation of f of s. Something like f of s times s squared plus 5 f of s equals 2. And out of this, that's an algebraic. It's not differential. You don't see f prime. Okay, you can solve for f of s. It's very algebraically skilled. It's going to be 2 over, for example, s squared plus 5. So you can explicitly solve for f of s. Okay, so when you find f of s, remember f of s is the Laplace transform of the unknown function. So if I can find f of s, then I can use the inverse. So for each transform, there is the inverse. So this is the Laplace transform, and this is the inverse of that. Basically acts, the other direction. So if I have f of s, I do Laplace inverse, and I get my f of t. Boom. Simple as that. So that's the big picture, okay, of what's going to happen. All right. So now let's start finding Laplace's, a bunch of functions. So let me again write down the definition. That was just an introduction of how Laplace, started, what was the motivation, and then how it works. So definition. Consider function f of t for t bigger than or equal 0. Okay. Then Laplace transform of f of t. So in parentheses, that Laplace transform is called capital F of s, is defined as, so that's the definition we're going to be using, at least for the rest of this class. It's the F of s. They also use this symbol. It's like the, bold, or, math bold of L. It's basically L, but they write it like this. If you look at the textbook, they write it like that. So Laplace f of t is defined as 0 to infinity e to the negative st times f of t dt. And I want to emphasize again, this integration is done with respect to t, right? And s is a constant where s is strictly bigger than 0, right? And s is a variable. Like, you don't have to worry about, plug in a value for s. It's again a function of s, independent variable s, right? Okay. Any questions before we start, finding Laplaces of maybe simple functions? And by the way, of course, it's integration, so we're going to need your skills on integrating functions, mostly by parts. Once in a while, maybe a substitution. We're gonna confront them today. Okay. Before continuing, I want to ask you this question. I want to take it back to Calc 1. What's the limit of t raised to 1,000 over e to the t as t approaching positive infinity? What's that limit? Basically, you have a power function and you have an exponential function. The question is, which one grows faster? The answer is exponential. So some people answering 0, which is correct. That means it doesn't matter what the power of t is. So even if it's 1 billion, it's still exponential function is going to beat this function at infinity. Remember, infinity. For some lower values, maybe up to 100 or 1,000 for t, the power function would beat it, but eventually at infinity, e to the t beats it, with a big difference. So no matter what the power of t is, when you divide it by an exponential function, of course, t has to be positive. It's 0, okay? So having said that, let's start finding Laplace of some functions. So examples. Let me write it like books. So the first function we're going to find Laplace for is 0. What do you think Laplace of this function is? Let me write down the formula. It's 0 to infinity, e to the negative st. So instead of ft, you plug in 0. It's going to be dt. What's that multiplication? 0. And integration of 0 is? Definite integral is 0. Indefinite would be constant, but constant minus constant is 0. So let's go back to our machine or transformation. If the input is 0, the output is also 0. So if f of t is 0, you output f of s as 0. Okay. Let's go to the next number. So this time, let's find the Laplace of 1. So we're going to see what is the output when input is 1. Well, by the definition, is 0 to infinity, e to the negative st times 1 dt. Okay. That's 0 to infinity, e to the negative st dt. What variable are we integrating with respect to? Because there are two of them, s and t. We are integrating with respect to
T.
T. Beautiful. So s with respect to t is a
Constant.
constant. So it's like, you're integrating e to the negative 5t, right? Maybe you want to use substitution, but I think we're better than that. So, the integration of this is going to be negative 1 over s e to the negative st, and then we evaluate it from 0 to infinity. And of course, I have to use the improper integration notation, but, you don't have to. Taking limit of this as t approaches. So again, remember, these two limits are the limits for t. So t from 0 to t to positive infinity, okay? Or to be more precise, we should say when t approaches infinity. Okay. So let me go ahead and rewrite it this way. This is negative 1 over s, which was a constant, okay? 1 over e to the st, I'll write it like this, and evaluate it from 0 to infinity. And remember, s is a positive value. I have a question for you now. What is the value of 1 over st when t approaches 0? The answer is I'm going to repeat it again. The limit of 1 over e to the st when t approaches infinity. Assume s is 1. It's 0. Right? Remember, denominator just keeps getting larger and larger. All right, and when you plug 0, it's simply 1. So we got 1 over s. Beautiful. So the f of s, right, again, the transformation, the Laplace transformation of 1 is 1 over s. Okay? All right. Let's talk about a theorem. It's going to help us. Because, someone might ask, well, what is Laplace of 2? Well, this theorem is going to help us. Theorem? I'm not going to write down, details. Just, let f of t and g of t be two functions. In fact, I can extend it to any number of functions. Two functions. And let a and b two constants. Then the Laplace of a times f of t, b times g of t, basically a linear combination of two functions with some constants. Literally, it's like, well, find the Laplace of f of t, then multiply by a, find Laplace of g of t, and multiply by b, right? Or in other words, if you're doing Laplace of c times f of t, you can simply pull out that constant. And of course, this is also true for subtraction. Okay. So only works for addition and subtraction. Later we'll see it doesn't work for multiplication of two functions. Okay. So that's 1, 2. Now we can answer this question. What is Laplace of 4, guys? Well, 4 is 4 times 1. 4 is a constant, can be pulled out. So it's 4 times Laplace of 1. We already know Laplace of 1 is 1 over s, so this is 4 over s. So in general, one can say Laplace of k is simply k over s when k is a constant. K is a constant. All right, questions so far? And by the way, in terms of Laplaces, okay, I'll tell you there's a similar table in your textbook, but so we can draw this table when on the left side you have functions of t, and the right side you have functions of s, like the Laplace transforms of them. So we already know Laplace transform of 0 is 0. If it's 1, it's 1 over s. In general, Laplace of k is k over s. Okay. In fact, this row alone, generalizes those two. It basically includes those two cases, because when k is 0, it becomes 0. And same thing with that one. Okay. Now we're going to go to some other types of functions. Okay. So maybe, we can keep this here and then add to it. We'll see. All right. The next function I'm going to use to find the Laplace transform of is exponential function. So I'm going to find the Laplace of e to the t. Now let's generalize it. Okay, so multiply t by any constant. So let's say e to the at, right? Where a is a constant. So a is again a constant. All right. Let's use a formula: 0 to infinity, e to the negative st. That was, the whole part of the formula, times the function e to the at, and then dt. I'm going to again emphasize, the only variable in this integration is t. S and a are constants, okay? So let's put them together. Becomes e to d. If you agree, you can write this as a minus s, right? T d to the dt. And, similar to e to the 5t, it's 1/5 e to the 5t. So this is 1 over a minus s e to the a minus st, 0 to infinity. That's the antiderivative of that function with respect to. Anybody has a question? It's obvious, right? If you derive this with respect to t, the a minus s goes down, cancels out the one in the denominator, and get the same integrand. All right. Now, here we need to put a condition. Remember, I would like the exponent of e, I want the exponent of e to be a negative number, so that when I plug infinity, it's 0, right? I want something like that, so that if I plug infinity, it simply goes to 0, okay? All right. So meaning, in this term, right? Let me write it this way, although it's wrong, but so if you evaluate it at infinity, it's 1 over a minus s, okay? E to the a minus s times infinity, and then minus e to the 0, which is 1, okay? Now, we would like this guy to be approaching 0. For that to happen, we need a minus s to be negative. That means we need to have that s should be bigger than a. But, we can throw that condition. So let's say if I wanted to find the Laplace of e to the at, then we find the Laplace and then we include this extra condition, okay? All right, so if that happens, if this happens, then that goes to 0. So we're going to have negative 1 over a minus s. Let's, push that negative into the denominator. So overall, so that this is what we got. Natural of, sorry, not natural. Laplace of e to the at is 1 over s minus a. Okay, so let me write it down here, 1 over s minus a, and in parentheses, s should be bigger than a, right? For example, Laplace of e to the 2t is 1 over s minus 2. Simple as that. Laplace of e to the 7t is 1 over s minus 7, right? Laplace of e to the negative 3t is 1 over s plus 3, correct? And let's put them all together. What's the Laplace of 7 e to the 3t? Okay, So what is 7? It's a constant. So we said if it's a constant, we can pull it out of Laplace. So it's going to be 7 times Laplace of e to the 3t. But we know how to find Laplace of e to the 3t. So this is 7 times 1 over s minus 3, which gives us 7 over s minus 3. Right? Okay. How much time do we have? 20 minutes. All right. I think I can talk about the next thing. Before continuing, let me tell you, the next one I'm going to find is the Laplace of a power function. So in general, I want to find this guy. Okay. But before that, let me define the function and let's play with it a little bit. The function I'm going to define, definition, it's called gamma function. People who have had statistics, they have probably seen it and heard it before. It's, the same function that generates the gamma distribution. And that's a definition. It's very simple. Gamma of x, that's the, capital letter for gamma, equals 0 to infinity. It's very similar to the Laplace formula, but it's a bit different. There's no function. The only variable is x here. E to the negative t, and then t raised to x minus 1 dt. Similar to Laplace, the variable of integration is dt, and x is a constant inside this integration. But the final answer is going to be a function of x. That function, we call it gamma of x. Okay? All right. And then one of the, big usage of gamma is factorial, and I'll show you how. You can state, factorial in terms of a gamma function. Let's start by, so we're still talking about gamma function. Let's find gamma of 1. Okay, gamma of 0. We'll take a look at that later. Let's find gamma of 1. Okay, so what does that mean? That means in this setup, x is 1. Okay, if x is 1, you have 0 to infinity, e to the negative t. So I'm plugging 1 for x. It's going to be t raised to 1 minus 1 dt. Okay. And let me erase this guy so you don't have to worry about, wondering what it says later. Well, t to the 0 is 1, so we have 0 to infinity, e to the negative t dt. This is a simple integration, right? It's negative e to the negative t, 0 to infinity. So same argument, when you plug infinity is 0, and when you plug, 0 becomes minus 1, which is 1. So let me erase this piece here. So gamma of 1 is 1. All right. Now here's a nice property. Let's look at gamma of x plus 1. So basically in that formula, I want to replace x with x plus 1. I'll write down details. So it's 0 to infinity integration, e to the negative t raised to. So instead of x, I'll replace it with x plus 1. I am still subtracting 1, dt. Okay. That becomes 0 to infinity integration, e to the negative t. So 1 and negative 1 cancel out. We have t to the x dt. Now, am I going to be able to find this integration? Hell no. Okay. I'm not going to be able to find the value of this integration. Of course, this is going to be a function of x. But we're going to use sort of induction, right? And write it in terms of the gamma of the next x, or, 1 less than x plus 1. You'll see what I mean when I start doing it. So I'm going to do this integration using by parts. So by parts. And if you can remember, by parts was basically saying, well, assume this integration is u dv, where I'm going to assume u is t to the x, and dv is e to the negative t dt. Then you differentiate that one with respect to t, remember. So you get du. It's like you're differentiating t to the 5th. What's derivative of t to the 5th? is 5t, and then you subtract 1 from the power. So in this one is going to be x powered down t raised to x minus 1 dt. Antiderivative of this one, we know it. That's, except that's v, guys. So let me make it sharp. V, so it's negative e to the negative t. Okay. By the by parts formula, this is uv minus integral of v du. Okay, uv. uv is negative e to the negative t, t to the x. You know what? Let me write it this way. Negative t to the x, e to the negative t. Of course, you have to evaluate from 0 to infinity. Minus v du. Already v du is a negative, so the negative in the formula becomes positive. Integration 0 to infinity. E to the negative t, right? There's an x in there. I'm going to pull that x because remember, the integration is with respect to t, so x is a constant. Let me put the x behind the integration, and then I have t to the x minus 1. Now this is the gamma function. What's the gamma function? Well, gamma function of what? That's exactly gamma function of x. So the second term is x gamma of x. And this guy is 0, interestingly. Think about it. This is negative t to the x over e to the t, right? Of course, if you plug 0 for t, 0 to the x, that's 0. And if you plug infinity, the denominator beats the numerator, so, eventually 0. So you have 0 minus 0, which the whole thing is 0. So this whole thing, is 0. So summarizing this whole piece, we got gamma of x plus 1 is x gamma of x. All right. Now you can see the factorial showing up. Here's the reason. Let's assume let n be an positive integer. Positive, okay? Like 1, 2, 3, 4, so on. Let's do the example and then we'll do the generalize. Let me say this. For example, let's do a small number, n equal 4, okay? So I'm going to find gamma of 4. Well, according to this guy, this is 4 times gamma of, gamma of 4, is gamma of 3 plus 1. So according to that, that's 3 gamma of 3, right? Basically, gamma of any number is the number, like one less number times the gamma of one less number, right? So gamma of 4 is 3 gamma 3. Gamma 3 itself is 2 gamma 2. Gamma 2 is, 1 gamma 1. But we already found gamma 1, so that's a nice thing about it. So this is 3 times 2 times 1, which is 3 factorial. So gamma of 4 is one less number factorial. So by the same argument, we can see gamma of n plus 1 is n gamma n. Use the same. So it's going to be n minus 1 gamma of n minus 1. Keep repeating this. Equals. So eventually you get, n minus 1, 2, 1, and then gamma of 1. Gamma 1 is 1, and as you can see, the rest is exactly n factorial. So gamma of n plus 1 is n factorial. Okay? All right. So for example, gamma of, 6 is 5 factorial, which is 120. Gamma of, bigger number is going to make a mess. So gamma of 7 is 6 factorial. That one is 720. But, you get the point. All right. Now that we talked about this, we can go ahead and find the Laplace of t to the a. All right. Gamma of t to the a. Well, let's apply the formula. It's going to be 0 to infinity, e to the negative st, right? And then t to the a dt. Good? All right. How am I going to do this one? I'm not going to do by parts. Because, when you do by parts, it's going to be t to the n minus 1. It's not very useful, right? So it's like you're finding Laplace of t raised to a minus 1. Remember, you're going to get a function of s eventually. What I'm going to do, I'm going to do this integration by, normal substitution, by substitution. And this is what I'm going to do. I'm going to let u be st. First of all, t equals u over s, right? And that means dt simply is du, over s. Remember, s is a constant, okay? S is a constant, and we know s is bigger than 0, okay? S is bigger than 0, so for t between 0 and infinity, we can see u is also between 0 and infinity, okay? Because of this definition right here. All right, let's substitute. So we get 0 to infinity, e to the negative u, right? So t was u over s, so this is u over s to the a, and dt was du over s. So in the denominator, you're going to have s to the a, another one. You have s to the a plus 1. That's a constant. Let's pull that out. So we get s raised to the a plus 1. Okay. And then the integration, 0 to infinity, e to the negative u, u to the a, right, du. Good. Let me write this way. You know what? Maybe we should have defined, used x instead of u. Let's just quickly switch u with x. Okay, so it's going to be 0 to infinity, e to the negative x raised to d. So I'm gonna, you know what? Let's keep it the same. So forget about this. So 0 to infinity, e to the negative u. Let me write this as a plus 1 minus 1 du. All right. On the side here, I'm going to write down the formula for gamma of x again. So gamma of x was 0 to infinity, e to the negative t, okay? T raised to the x minus 1 dt. Now I want to ask you guys, what is that in terms of gamma function? In fact, what's the input of gamma? This is equal to gamma of a plus 1 is correct. I purposely wrote it this way. Remember, the power of t, here t switched to u. It's the same integration. So it's gamma of a plus 1. So at the end, this is what we proved. That Laplace of a power function t raised to constant a is gamma of a plus 1 over s raised to the a plus 1. Okay? Now, the reason I'm not writing this as a factorial, remember, factorial is only defined for integers. 2 over 3 factorial doesn't make sense. So that's the reason the gamma function is defined. And, when you have a constant a, which is not integer, you can simply write it as gamma function of a plus 1. So that's the reason we're using the gamma function notation here. But if it's integer, we can use the factorial. For example, let's see, what's gamma? Let's, do the simplest one. Gamma of t to the first, right? So it's going to be gamma of 2, right, over s squared. Remember, in this case, a is 1, right? So it's going to be a plus 1, which is 2. And gamma of 2 simply is 1 factorial over s squared, which is 1 over s squared. So Laplace of t is 1 over s squared. Let's see what the Laplace of t squared is. Well, according to the formula, is gamma of 3 over s cubed. Gamma of 3 is 2 factorial, so it's 2 over s cubed, right? So in general, if t is raised to n, now n is an integer, not just any real number, then it's gamma of n plus 1 over s raised to the n plus 1, which is n factorial over s to the n plus 1, right? So one more example, s to the t raised to the 7th, for example, right? Laplace of t to the 7th is 7 factorial over s to the 8th. 7 factorial is a big number, don't worry about it. So you can keep it like that, okay? All right. So let me summarize. I'm not able to finish 10.1, so we'll continue for the rest of that on Monday. We still, want to figure out, for example, what's the Laplace of sine of t, Laplace of cosine of t. Remember, you want to find the Laplace of, someone is saying 2 factorial. Which one are you talking about, Alex? You're talking about this one? Yeah, it is 2 factorial, correct, but 2 factorial is 2, so that's why I wrote 2. Sorry, I skipped a step. All right, but you guys can keep it in factorial form. Anyway, so remember, we want to be able to find the Laplace of whatever functions that we're going to encounter, right? Trig functions, exponential functions, polynomials. These are the big 3 categories of functions that we deal with. And maybe, hyperbolic functions, Laplace of, sine h of t. Laplace of, why not, like tan of t. Laplace of secant of t, okay? So we'd like to find the Laplace of all these functions. So for the rest of that, we'll continue on Monday. Let me tell you about one, simple function, which is piecewise function. And, let's talk about the step function. Okay. The picture of a step function in general, or called floor function, if you can recall, it was like that. Do you remember that bracket of x, which always was the integer? I mean, depending on in some textbooks, they go like that, and floor function, they go like this. Like that's the integer above, that's the integer below. Anyway, so any function of this form, and it doesn't have to be, increasing steps, like just stepping, like steps going up, but just down. Could be all over the place. But they cannot overlap each other. Like you can't have this case. That's not a function. Remember that? It has to satisfy the vertical line test. So for functions like that, we can also find the Laplace. So let me go to one example. As long as you have the equation of the function, you can find the Laplace. So I'm looking at question number 8. Okay, so the function given is this guy. So it's like it's bold here. Okay, and then it's like that, and then the rest of that goes down to 0. So it's something like that. This is number 8. So this point is 1, 1. Let's not write down details. So this is 1. Okay, if this is t, this is the f of t axis. That's 1. Here's 1, and here is 2. Okay, what does it mean? Well, you can literally write down the piecewise equation for this function. So it's 0 when t is bigger than equal 0, less than equal 1. It's 1 if t is bigger than 1, less than equal 2, less than 2. Oops. bigger than 1, less than 2. And if t is bigger than or equal to 2, it's 0 again, okay? And you literally write down the formula for Laplace of a piecewise function. You would do 0 to infinity, right? And then e to the negative st f of t dt. But look, this function has 3 different values on 3 different subintervals, right? So it's like you break it down to 0 to 1, 1 to 2, and then 2 to infinity. But over the interval 0 to 1, the function is 0, so this piece is 0. Same thing for t 2 to infinity, that's 0, so that integration is 0 as well. From 1 to 2, the function value is 1, so you only have integration 1 to 2 e to the negative st 1 dt. And you simply, integrate it, which is negative 1 over s e to the negative st, and then evaluate it from 1 to 2, t equal 1 to t equal 2. Remember, for the infinity, we got 0, right? And you go ahead and plug 2 and 1 to the function, so we get negative 1 over s e to the negative 2s minus e to the negative s. So, that means the Laplace of that function is e to the negative s minus e to the negative 2s over s. And in fact, these are sort of the forms that you might encounter when you're doing signal analysis or circuit analysis in applications. So these are the type of functions they're going to deal with. So I've already assigned problems for 10.1. Only do the ones that is doable, okay? Like avoid sine and cosine. Only do polynomials. Let me write down the list here. I'm not going to modify the list on e-learning, so people have access to these notes. So you can do numbers. So 10.1. 10.1. Numbers 1, 2, 3, like 4. 5 is doable. 6 is not. Then 7. You can do the following ones all the way through 10, 11, 12, 13, 14, 15, 15. You can do these ones. Okay. So do that. No, I'll grade the quizzes, post the grades for the exams and quizzes. Any questions? We have 36 people. It's good. What time for exam grades? Dude, you're putting pressure on me. How about 9? Later. That's a very good answer. Later. Later. Thank you, Jacob. Okay, guys. Take care. Stay at home.